Welcome everybody to this edition of the ICTS String Seminar. Today we are very pleased to have Shiraz Minwalla from TIFR, and he's going to talk to us about the classical Regge conjecture from the bound on chaos. Okay, over to you, Shiraz.
Okay, so thank you for the invitation. It's always wonderful to speak at ICTS, even if virtually. Actually, this is my second virtual seminar in ICTS. I did one from far away 4 years ago. The technology now is better. Okay, excellent. So my talk today is titled the Classical Regge Conjecture from the Bound on Chaos, and is based on this paper that appeared in the archive a week or two ago. And then for earlier background material, sort of largely for context, you can take a look at these papers. Okay, so let's start. It's very well known, as all of you know, that the UV behavior of unitary quantum field theories is constrained by several well-established bounds. For instance, there's this famous Froissart bound that tells you that the inclusive cross-section or the forward scattering amplitude, these are the same thing, in well-behaved quantum field theory, cannot grow too fast with energy. It cannot grow faster than than S dressed with some logarithms of S. Now, such bounds, which are well known, have been known since the 60s, constrain the behavior of quantum field theories or good theories in the limit that the energy is asymptotically large. That is, the energy is the largest scale in the problem. Now, it's sometimes interesting to study field theories with a tunable coupling constant. Let's call this coupling constant G. Okay, and we could then take the following limit. We could take the limit that G goes to 0, and then study energies that at 0G or very small G, as very small values of G, are large, but not so large as to become inverse powers of G. So large compared to 1, but not large compared to inverse powers of G. So, technically we could first take the limit G goes to 0, work in a power series expansion in G, and then look at the behavior of the scattering amplitudes, for instance, of this theory of each term in the power series expansion in G. Okay, now, one could study each term in a power series expansion in G, but of course the most interesting term is the leading order term. The leading term in this power series expansion in G is the term in which scattering amplitudes are governed by tree graphs without loops. I will sometimes call these classical scattering amplitudes. Okay, so we could look at the scattering amplitude for such generated by such graphs, as I said, at energies that are large if you keep just these graphs, and these correctly determine the behavior of the scattering amplitude of the theory at energies that are large compared to all the classical length scales, the length scales in the classical theory, but don't scale like inverse powers of the coupling constant, for instance. Okay, so this regime of energies large compared to 1 but small compared to 1 over G in some appropriate unit exists provided you've got a parameter like G which can be made parametrically small. Okay. Now, as I said, the famous bounds that constrain the high energy behavior of theories constrain what happens at arbitrarily large energies. And energy is large compared even to, say, that 1 over G scale. However, when G is small, there's this new parametrically large regime where you can, where it makes sense to ask how something scales because there's an infinitely long range for the scaling. And so one might wonder whether there exist independent constraints on the high energy behavior of scattering amplitudes in this intermediate regime. So on the high energy behavior of scattering amplitudes in this classical high energy regime. Oh, sorry. Now, in a paper written about a year ago, my collaborators and I made the following classical Regge growth, the CRG conjecture, following on suggestions that have been made by many people over the last few years. And the statement of the conjecture is that classical theories whose S matrices grow faster than S square in the Regge limit are unphysical. So all physical theories have S matrices that in this intermediate classical regime never grow faster than never grow faster than s squared. They grow like s squared slow. In the paper in which we sort of formulated this conjecture that, as I said, had been said before in various ways by other people, in this paper, we demonstrated that if this conjecture was true, then it acts as a powerful constraint on classical theories of gravity. For instance, one of the things we showed is that in dimension 6 and lower, the unique classical theory of gravity, keeping all terms that are Riemann to the 4 or lower, saying nothing about Riemann to the 5 and higher terms, the unique classical theory of gravity up to Riemann to the 4 terms, and therefore the unique classical 4 graviton S matrix, the unique such theory is that of Einstein gravity, and the unique S matrix is the one that follows out of classical tree-level diagrams from Einstein gravity. Okay, so this sort of makes, this is sort of like an existence proof for the statement that these bounds on this scaling in this intermediate or classical regime are interesting because they lead to interesting consequences. Okay, so this for me is motivation to go further and try to study more carefully whether or not this conjecture, the CRG conjecture, on which our results for classification of gravitational theories were based, is indeed true or not. As far as I'm aware, there are 3 strands of evidence in support of the CRG conjecture. I will now list these arguments in order of increasing strength. Okay, the first argument is just to look around and look at consistent examples of theories that you know of and check whether CRG works. So most classical theories that we know for sure to be good consistent theories are 2 derivative theories. And these are theories where usual canonical quantization works. They have the usual canonical structure, Poisson brackets, can be lifted up to quantum theories. 2 derivative theories, at least large classes of 2 derivative theories, we're pretty sure make sense as classical theories and often as basis for building quantum theories. Okay, now if we look at any 2 derivative classical theory, it follows immediately from dimensional analysis that the CRG conjecture is true. You see, the CRG conjecture is about the Regge scaling of a scattering amplitude. It's about the scaling of the scattering amplitude in the limit that S is taken large at fixed t. Now, suppose we take a 4 scattering amplitude in a classical 4 classical scattering amplitude in a 2 derivative theory. There are 2 kinds of such amplitudes. This one generated by contact graph, but since this amplitude is 2 derivative, it is of homogeneity S in energy. So it's some function of either S or T, and therefore cannot go faster than S squared. Things are a little more interesting with the tree-level exchanges, because once again, the net dimensionality of a tree-level exchange graph is that of energy squared, that of S. But we could have more rapid growth in diagrams that grow like S squared by T. Such graphs are still of dimension S, but they grow like S squared at fixed t because you allow for a t-pole. And indeed, this is what happens in gravity. The gravitational scattering amplitude saturates the CRG conjecture. It grows like S squared by t, so it grows like S squared fixed t. Okay, so far so good. So it just is a trivial consequence of dimensional counting that the CRG conjecture is true for classical theories. Classical 2 derivative theories. Now, what about other classical theories that we know to be good? Well, there's basically one other theory that I sort of feel sure is a good classical theory, and that's string theory. And then if you look at the Wheeler-Shapiro amplitude in string theory, you find that it grows like S squared plus 8 times t, where A is some number. And the important thing about it is that A is a positive number. Now, for physical scattering amplitudes, t is negative. So the S squared growth of Regge growth of Einstein gravity is ameliorated, is weakened by stringy effects, also satisfying the CRG conjecture. Okay, so this, of course, is a very weak argument, but at least it's a sanity check. All the classical theories that, at least I feel I know for sure to be consistent, appear to obey the CRG conjecture. Now, a more serious argument for this conjecture was presented in the CEMZ paper. I will give you a very rough review of it, and I hope I don't maul the argument. In their paper, the CEMZ, in Appendix D of their paper, where they talked about this signal model, CEMZ argued that 1 plus I times S of delta S divided by S must obey the inequality that the modulus of this object is less than or equal to 1. Now, what are all these objects? It's not completely clear what they are in the text of that paper, but very roughly speaking, I think you should think of this scattering amplitude as the S matrix to pass through a shock wave, or roughly speaking, the S matrix in energy and impact parameter space. Okay, so then there's an argument given that this T object, which is 1 plus I times this blah blah blah, has modulus less than or equal to 1. Now, suppose we work with the classical limit, where the S matrix is proportional to a very small parameter, and so should be taken only at leading order in that parameter. In this limit, this inequality turns into the inequality that the imaginary part of this S divided by S, where this is the energy, is greater than or equal to 0. That's how the real part of this to leading order in G will be less than 1. Okay, now suppose you've got a scattering amplitude that at high energies scales like some coefficient times S to some power of power which is perhaps a function of this delta. Now let's suppose that this S, which is a complex number, has a modulus mod S and a phase e to the power I phi alpha. Okay, then plugging this behavior into this formula here, okay, we find that we get the condition that that's some number times the sine of A delta minus 1 times phi must be greater than or equal to 0. Oh, and I forgot to tell you that the argument was that this inequality should hold everywhere in the upper half of the S complex plane. Okay, so this inequality should hold for all phi that lie between 0 and pi. But you see immediately from here that if A delta is greater than 1, then no matter what the sign of this T delta is, it's impossible for this quantity to be to have the same sign, or therefore the positive sign, for all phi between 0 and pi, because if A delta is greater than if A delta is greater than 2, then A delta minus 1 is greater than 1, and so phi the argument of the sign varies over a range greater than pi, and so the sign function changes plus minus sign as phi varies between 0 and pi. And so it follows from this that if this inequality is to be true, the high energy behavior here must be with a power that is less than or equal to 2. Okay, so this requirement here tells you that the S matrix in sort of this impact parameter space as a function of S cannot grow faster than S squared. And then I suppose Fourier transforming this from impact parameter space to T space would tell you that the S matrix as a function of S and T also cannot grow faster than S squared.
So Shiraz, in this argument that you gave, where did you use the fact that S had to be large? It almost seemed like this argument applies for all S. The previous one, that A delta is smaller than 2, seemed to apply for all S.
A delta is smaller than 2.
No, you said you said it grows at large, but in principle you could write this at any S, right? At any mod S, you could write this expansion.
Yeah, right. If Sasha Zhibodev is here, maybe he can take this question.
Yeah, I'm here. I can take this question. So in deriving this argument, which came from unitarity and causality, it was important to separate the effect from time delay or advancement from crossing the shock wave from the effects of the wave packets spreading and things which would prevent you to conclude there is a problem. And the result of this analysis is that you can only, so Shiraz wrote this inequality, which is something less than 1, I think, above.
Yes.
So I think if maybe a slightly more precise version of this is that it's less than 1 plus corrections which do not grow with S. So if you can add, if you violate this inequality by things which which do not grow with S. So like something like phi cube, it's not necessarily a problem. So it's really only the argument which allows you to talk about things which grow with S. I don't know if it was the question, but
yeah, no, I think that answers the question. So you're saying this inequality, effectively, I should think of it as a large mod S inequality.
Yes, well, it is not too large because the correction is still small. So we are not going to the regime where the amplitude is large. So S that Shiraz has on the slide is still small. But as a function of this little s, it's a growing function. So it's, as you go to larger s, you start entering the regime where things become largish. So it's not large, but it's.
I see.
It's this intermediate regime I was talking.
It's yeah, exactly.
S large in classical units, but not large compared to the coupling.
Okay, thank you.
Yeah. Okay, excellent. So this argument is a beautiful argument, but it seems to me to be sort of more intuitive than completely precise. For instance, the transition from impact parameter space to momentum space may involve subtleties related to delta functions with terms in impact parameter space. Such contributions can and do arise from local bulk contact terms, which are of central interest to this paper, to this talk. Sorry. So I'm going to have nothing more to say about this argument. It would be wonderful to take this and make this a theorem, but that's not going to be my direction.
One question.
Yeah.
So in this the slide above, you had A, right? And could A also be negative or not?
Could A be negative? Well, given what Sasha says, it's only things that grow with large S that are problems. So if this is the A you were talking about?
Yes.
Yeah, so I think that he would not mind anything that does not grow with S.
Okay, thank you.
Okay, but this argument, though, is not going to be the topic of my talk today. I'm going to try to argue for this CRG conjecture from a slightly more precise starting point, namely the chaos bound. Okay. Now, it's been suggested by many people, including the authors of the original chaos bound paper, that the chaos bound, that the results of the chaos bound paper suggest a CRG type bound on scattering amplitudes. Okay, the point of this talk is to make that suggestion precise in a particular context. Okay. In my opinion, the strength of the arguments I will present in this talk is that the arguments are precise and that they follow from a well-established starting point, namely the chaos bound, which is more or less a theorem in quantum field theory. The weakness of the argument is that it's going to be a rather Baroque argument, in the sense that in order to try to establish some result about scattering in classical theories in flat space, what we will need to do is to invoke a large superstructure. We need to invoke the structure of ADS CFT, ADS spaces, conformal field theories, and so on, unitarity of the boundary theory, in order to prove something that looks like a simpler statement in a simpler theoretical setting. And that's a weakness, and one would like to get beyond that. But this is the context of my talk. Okay. So so in the rest of this talk, what I'm going to do is to just present the arguments that we have given to try to establish this that the CRG conjecture necessarily follows from the bound and chaos in a particular setting that I will make clear. Okay, so let's go. To start with, what I'm going to be working in the context of the ADS-CFT correspondence. My field theory is on a boundary ADS cylinder, it's a global ADS space, and there's a bulk theory that lives in the bulk of that ADS space. When I'm going to need to write formulas for such things, I will work in embedding space in embedding space. So my dimensionality is as follows. I work with the d-dimensional field theory, a d+1 dimensional ADS, and this d+1 dimensional ADS is embedded in a d+2 dimensional embedding space, which has 2 times. So it's an RD, 2. Okay, boundary points, as are usual in this embedding space formalism, are parametrized by null rays in this embedding space. Okay, and through this talk, I'm going to study a 2-parameter set of 4 boundary point insertions. These 4 insertions are at the following 4 boundary points, where the first 2 coordinates in embedding space are time, and the remaining d coordinates in embedding space are space. Okay, now for those of you who are not too familiar with embedding space, it doesn't matter, because this tau is just simply the usual familiar global time of ADS. And these 2 coordinates together parameterize an angular direction in the spatial past on the boundary, parameterize an angular direction in the spatial part of ADS. Okay, so you can think of this, the insertions that I'm looking at, you can think of as follows. Okay, you can think of my 4 points, 1, 3, and 2, 4, to be inserted 2 points, two insertions at early times and 2 insertions at late times. The 2 insertions at early times, this time is a variable, it's called tau, but you could imagine it being around 0 to start with. These 2 insertions are at angle theta equals 0 and angle theta equals pi. So P1 is at 0 and P3 is at pi. Okay. The remaining 2 insertions are at a fixed later time. This time is global time. This fixed later time is pi. Okay. And they're rotated compared to the original insertions by the rotation of an angle theta. Okay. So P4, if theta was 0, P4 would be just above P1 on this ADS cylinder, and P2 would be just above P3 on the ADS cylinder. Theta gives you the extent of rotation for the P1, P3 versus P4, P2. Okay. Precisely this set of insertion points, or something very closely related, was used in the bulk point singularity paper from 5 or 6 years ago, and you'll see why this is useful. These insertions are useful for me. Notice that these insertions have 2 parameters in them, tau and theta. Okay, so by varying tau and theta, I get a 2-parameter set of kinematics of operator insertions. Notice 2 is also the dimensionality of the set of independent cross ratios. So by varying tau and theta, I'm exploring an open neighborhood in the space of cross ratios of the CFT. I'm not doing something very exceptional. Okay. Now, it's going to be of importance to us to understand the causal relationships between the various insertion points in our theory. Okay. The precise causal relations depend on the values of these insertion parameters, tau and theta. To start with, suppose tau was 0. Suppose tau was pi. So that P1 and P3 were on the same time slice as P2 and P4. Then it's sort of clear that the 4 points are related, you're related in a Euclidean manner. Okay? So, in fact, if you look more closely, you will find that if tau is, it doesn't have to be all the way up to pi. As long as tau is greater than pi minus theta, the 4 points are related in a Euclidean manner. All 4 points are space-like separated from each other. And this regime of parameters, tau greater than pi minus theta, through this talk I will call the causally Euclidean set of configurations. Okay, the cross ratios in this causally Euclidean set of configurations lie on the principal sheet. They're just simple analytic continuations without having passed through a branch cut from Euclidean correlators. Okay, now imagine starting at tau equals pi and slowly decreasing tau. So as we go through this value, as tau goes below pi minus theta, some causal relations change. And the causal relations that change are that now, instead of all 4 points being space-like separated from each other, P4 is in the causal future of P1 and P2 is in the causal future of P3. Okay, so there's now time enough for a light ray to go from P1 to P4, which was not the case when P1 and P3 were too near in time to P4 and P2. Okay.
Hello.
Yes.
Shiraz.
Yes.
Just can I just ask a question? So when you're talking about causal relationships, you're talking about causality from the boundary theory or from the bulk?
I'm talking about causality from the point of view of the boundary, but this is presumably the same thing. At the moment, I'm just talking just from the boundary. Yeah, it would, I think, be the same thing. This is plain empty ADS. Okay.
Okay, thanks.
Yeah. Okay. Excellent. Yeah. Now, as we further lower tau from pi down to 0, there's another point, that is when tau goes less than theta, when the causal relations change again. Okay. Now what happens is that both P4 and P2 are in the causal future of both P3 and P1. So this is easiest to see at, let's say, when tau is 0. Now there's enough time for a light ray emanated from here to reach a light ray at any of these points, because you have time tau available. So that's enough time to go an angle pi, which is the whole sphere. Okay. So there's another switch in causality when tau goes below theta, and in this regime where tau is below theta, these 2 points are in the causal past of these 2 points, right? So we have 3 causal relations, all 3 space-like separated. In the middle, this the causally Regge regime where P4 is to the future of P1 and P2 is to the future of P3, but let's say P3 and P4 would be space-like separated. And then the last one, this causally scattering regime, in which the 2 bottom points are in the past of the 2 top points. Is this clear? Any questions about the causal relations in kinematics? Okay, great. So as is usual in the study of conformal field theory, when we go from one causal patch to the other, we take some insertion point through the light cone of some other insertion point. And that process, as is usual in the study of conformal field theory, that process tends to take you from one sheet on the space of complex conformal cross ratios to another sheet on the space of complex conformal cross ratios. And I'm going to describe for you in some detail now precisely how this happens. In order to understand how this happens, it's important to I epsilon correct our theory. So imagine that the time that we have, our global time has been obtained from analytic continuation from Euclidean time. And we've done this analytic continuation not by 90 degrees, but 90 minus epsilon degrees. Okay. Following through that logic will tell you that the insertion points are not exactly what I told you before, but are I epsilon corrected, because the time gets a small imaginary part. Okay. And when you use these I epsilon corrected points, you can work out the formula for the conformal cross ratios corresponding to these points insertions. And you find formulas for the conformal cross ratio Z and the conformal cross ratio Z bar that are given by this expression 9 here. For some purposes in my talk, I will use not these conformal cross ratios Z and Z bar, but instead sigma and rho, where sigma and rho are defined as follows. Z is defined to be sigma e to the power rho, and Z bar is defined to be sigma e to the power minus rho. These sigma and rho will often be more convenient for me than Z and Z bar. It's just a simple field redefinition of Z and Z bar. Okay. So now I introduce.
Hello?
Yes.
So sorry, Shiraz, sorry to interrupt again. So here the sigma is real and rho is complex, or
no. Okay. It depends on
both are
depends on where we are in this conformal cross ratio space. So when Z and Z bar are complex conjugates of each other, sigma would be real and rho would be complex. That would be imaginary. Okay, but when z and z bar are just real numbers, independent real numbers, then sigma and rho are both real. Okay, both are possible in Lorentzian space. You know, in Euclidean space, z and z bar have to be complex conjugates of each other. In Lorentzian space, you could have one or the other. On all our configurations, z and z bar are just real numbers lying between 0 and 1. And so both sigma and rho are real, ignoring the I epsilon connections.
Okay, thank you.
Okay. Yeah, so z bar is a bit of a misnomer. You know, I shouldn't be calling it z bar, but I'm just using standard terminology that everyone uses when they study these cross ratios, because where I'm interested in, then z bar is not the complex conjugate of z. And indeed, z and z bar will soon become independent complex variables. So it's a little stupid to call it z bar, but okay, that's what everyone does. So sorry for the confusion. Okay, great. So now I introduced all these I epsilon corrections so that I could tell you what's going on in complexified conformal cross ratio space. So let's imagine that we start with our configurations. We start with our insertions at yes.
Yeah, when you introduce these epsilons, you are picking an ordering also, right? So they are time ordered.
Right. I should have said that. All my insertions, I'm always studying time ordered insertions. All through my talk, I'm studying only time ordered insertions. Okay, that's a choice. It's going to be a very useful choice because, you know, time ordered insertions very naturally tie up with S matrices, as we know from the LSZ formula. So it's going to be a useful thing to do, but this is just a choice. But other questions? Okay, excellent. Right. So now imagine that we started with our tau, which is at pi, and then we slowly lower tau, below this to go first below theta, and then first below pi minus theta, and then below theta. The question I'm going to ask is what happens to the conformal cross ratios as I do this? So if we ignored the I epsilon corrections, it's very easy to see that as I start with some value of z which happens to be equal to z bar. I start here with some value of z which happens to be equal to z bar, and then as I lower tau from pi down to pi minus theta, z bar hits 1. And then as I further lower tau, it starts coming back. Okay, so z bar goes to 1 and starts coming back. Now, this is an imprecise, that z bar goes up to 1 and starts coming back is an imprecise statement. Because correlation functions in a conformal field theory typically have branch cuts at z bar equals 1. So if I tell you that something goes to 1 and starts coming back, there are many ways that could happen. It could go around the branch cut 7 times and come back, or it just could go without going around and come back. So in order to resolve what actually happens, you need these I epsilon corrected insertion points and I epsilon corrected conformal cross ratios. And once you have them, it's very easy to see what actually happens. And in fact, what actually happens is that z goes up to 1, then circles the branch cut at 1 counterclockwise, and then comes back onto nearly the real axis. As we keep lowering tau from even further, so we lowered tau from pi, then we went down to pi minus theta. Now we come back to theta. All through this lowering process, z, okay, which started out here, goes and decreases towards 0. And then at tau equals pi, z starts coming back. Once again, that's an imprecise statement. Once again, the I epsilons help us to resolve what the imprecision is. And it tells us that what actually is happening is that the z circles counterclockwise around the branch cut at z equals 0 and comes back. Okay? So now we see what these 3 different causal regimes that I talked about were in terms of conformal cross ratios. The causally Euclidean regime is just the simple analytic continuation from Euclidean correlators. The causally Regge regime is the analytic continuation in which z bar is taken around the branch cut at 1 and brought back into this, the small regime. Okay, I've called this the causally Regge regime because this is precisely what happens in usual conformal field theory studies of the Regge limit. We'll come back to this. Okay. And finally, the causally scattering regime is the one in which Z bar has circled around its branch cut at 1 and come back here. But Z has also then gone around the branch cut at 0 and come back. Okay.
Sorry, Shiraz, can I just
please.
So where are the branch cuts? It's from between 0 and 1. You're taking a branch cut from 0, 1, 1 or 0 to infinity?
0. You could take the branch cut from 1 to infinity, for instance.
Okay, and what about the 0? And then
the 0 could also go to minus
0 to minus infinity. Is that how you're imagining it? No.
Yes. Oh, wait, am I imagining it here? I think so. No, maybe I'm imagining it. Just a minute.
Yeah, you're probably putting it from 0
to 1. Yeah, I'm putting it from 0 to 1. Yeah, it's probably going this way.
You go below you start from below the cut.
Yeah, right? You're probably right. You're probably. Both branch cuts are probably 0 to 1.
Okay. And just to if you can repeat again what you said about the different regimes. So you're saying the Z. So there's one regime which is where you start Z bar less than 1, little below the branch cut.
Yes. Then you circle around like this and come here.
Then you come here on the other. So it's on the top sheet.
On the top sheet, exactly. You're right. Yes. On this sheet, we've gone round this branch. We start in the Euclidean sheet and then come like this.
Okay. And the other one was the Z, which you're saying.
Yeah, Z goes here and circles around here and comes here.
Okay.
Z is the purple curve. Z bar is the green curve.
And just spell out the regimes again.
Okay, so the first one, the one we started with, was the one in which all 4 points were space-like separated from each other.
Yeah.
Okay. Then the one where tau was between pi and pi minus theta. Where tau was between pi minus theta and theta. This was the one where Z bar has gone around the branch cut at 1 and come back, but Z has not done it. Okay. And the one where tau is less than theta, this causally scattering regime, is the one where Z has also gone around the branch cut at 0.
Okay.
Okay. This causally Regge regime is the one that people study in the usual studies of the Regge limit of conformal field theory. We'll come back to this. Okay. This has been studied before, but in the study of scattering or the study of the bulk point limit. Again, we'll come back to this causally scattering.
Yes, so there is one Euclidean correlation function, and if you just continue that Euclidean correlation function in 2 ways, there are only like 2 distinct time coordinates here, I guess, tau and pi. So
yes.
So actually maybe it is so the Euclidean correlator, actually once you analytically continue it, you could just think of it as a function of tau and maybe one more time variable, and there are just 2 ways of continuing it, right? One in which you take one of the imaginary parts to 0 first, and the other in which you take the other imaginary parts to 0.
I didn't understand. Say that again, please.
Sorry, I was just saying that I'm saying something very trivial, but just to make sure I understand, when you start with the Euclidean correlator, you could take to get the right ordering, you just need to ensure that the ordering of the imaginary parts is correct, or ordering of the time part of the coordinate. The imaginary part of the time part of the coordinate is right? So this Euclidean correlator, once there are just 2 ways of analytically continuing it. And one of them gives you, I guess, causally Regge, and the other gives you causally scattering.
No, there's an infinite number of ways. You see, the branch sheet of this correlation function is, infinitely covered. And one way of understanding that is that if you're on this ADS cylinder, even if you stick to time-ordered configurations, particular ordering, okay, you could come back to the same conformal cross ratio as you move up the cylinder.
I see.
Conformal cross ratios only depend on where you are in embedding space. But the actual physical cylinder, ADS cylinder, is an infinite covering of embedding space, because the time which was periodic in embedding space is actually non-compact. Okay? And as you take things further and further away, you get different correlation functions. So the structure of these correlators is in general very complicated and involves an infinite number of branch sheets. I'm just studying 3 of them.
I see. Okay.
Okay. Yeah. Yes. And actually, the full branch structure of these correlators, I'm not sure has ever been completely characterized. But I think is an independently interesting question. because these branches aren't all independent. You can sometimes get to the same physical point by going through different branches. So there's some connection, it's like some complicated Riemann surface, not just some ever expanding.
But this complication is arising because you're in EDS and you have the fact that you have to unroll the when you.
That's one way of understanding it, but it's just a complication that is true of the analytic structure of conformal field theory correlation.
Right.
Yeah. Okay.
Shiraz, one question.
Yes.
How is it that your Z and Z bar are always between 0 and 1 real?
How is it? It's not true for all configurations you can write down on the cylinder, but we've carefully chosen, actually by following the bulk point paper, we've carefully chosen configurations for which it is true. So for instance, there is a particular point in this embedding space, which is the Regge point, where theta and tau are both 0. And you can blow up a neighborhood of the Regge point, and you'll see that there are, even in the neighborhood of that point, which lies in our class, there are elements where the conformal cross ratios go complex. Okay? It's just that we are choosing a particular set where this does not happen. So it's no more than...
Not necessarily complex, I'm saying.
It could also
I'm
become
just saying, they could be real, but larger than 1.
It could be real, but larger than 1.
So purely Lorentzian configuration, but perhaps that could be, that would break this symmetry and things like that.
Yeah, it's just not in the configurations I'm studying. There's no claim that these configurations don't exist. Okay, so our configuration should be thought of as an open neighborhood in conformal cross ratio space, not all of conformal cross ratio space. Right, and this is typically true of coordinate charts that people study. This row coordinates that people look at conformal field theory correlation functions, and it's also some open neighborhood in the space of configurations. It's not the whole thing. Okay. Great. But these set of configurations will be enough for my purpose, so I won't need to do it. Okay. Now we're looking at these insertion configurations, and 2 limits of these configurations will play a particularly important role for us. The first of these is the tau goes to 0 limit. Okay, so in the limit tau goes to 0, I've just simplified the conformal cross ratios for you here. And since there's no branch cut around the bulk point singularity, there's no interesting branch cut, at least that we will explore around the bulk point singularity. The I epsilons were not important for this, so I've omitted them. Okay, so this is what happens to the cross ratios when tau goes to 0. The important thing to note is that this rho coordinate, this rho conformal cross ratio, which is the ratio of Z and Z bar, more precisely, e to the power 2 rho is the ratio of Z and Z bar. That goes to 0 in this limit, which means that at tau equals 0, Z is becoming equal to Z bar. Okay, sigma is just something. It's given in terms of the angle. And since we're taking tau to 0 but not doing anything special with with theta, sigma is finite, rho is going to 0 in the limit that tau goes to 0. Okay. Now, why is this tau goes to 0 limit important or interesting? The tau goes to 0 limit is important and interesting for the following reason. You see, I told you that one nice way to think of boundary insertions in a conformal field theory are by parametrizing it by these insertions by the null rays in embedding space. Now, null rays in particular are vectors in embedding space. Just thinking of them as vectors in embedding space, we could ask the following question. If we take the span of all vectors that can be written as linear combinations of these vectors in embedding space, what subspace of embedding space do they cover? Well, so generically, these 4 P's are linearly independent, so you cover a 4-dimensional space. Since this space, whatever it is, includes null vectors, it can't be completely Euclidean. And it's not difficult to convince yourself that, this is enough of an argument to convince yourself that the 4-dimensional space spanned by these 4 P's could be either R3, 1, 3 space and 1 time, or an R2, 2, 2 space and 2 time. That's the generic situation. However, a 1-parameter tuning of coordinates in a generic situation can allow you to go to a place where the 4 P's, the 4 insertion P's, are not linearly independent. Okay. When that happens, the span of the vectors is not R3, 1 or R2, 2, but some 3-dimensional space. In fact, this happens with our insertion locations. When tau goes to 0, it turns out that P1 plus P2 plus P3 plus P4 is 0, as you can just explicitly check. Okay. Now, this is very special. Okay. This is very special because, as demonstrated in the bulk point paper, when this kind of thing happens, when a linear dependence of this sort happens, and when some certain other causal relations are maintained, okay, correlation functions can develop a singularity, called the bulk point singularity. Now, it's easy to show that whenever something like this happens, whenever a linear relation develops between the 4 P's, this rho always goes to 0. And indeed, this, as I've shown you, this happens, well, as I've told you, this linear combination of P's goes to 0 as tau goes to 0. But rho, remember, in the small tau limit was proportional to tau and also goes to 0 as tau goes to 0. So this is a consistency check of that. Okay. So the place where these linear relations develop is in conformal cross ratio space, a place where rho goes to 0. And when these relations develop and when certain other conditions are obeyed, which I won't even tell you about, but happen to be obeyed for our configuration, the correlation function develops a singularity in some inverse power of this cross ratio rho. Okay. This is just a teaser about this. I'm going to say much more about it, but fine. So tau goes to 0 is rho goes to 0. It's a place where you develop this new kind of funny singularity, which the bulk point paper called the bulk point singularity.
Shiraz,
yes.
Does this also happen on causally Euclidean sheet?
Causally Euclidean sheet? No, I don't. No, it doesn't happen. Yeah. So once again, rho goes to 0 on the causally Euclidean sheet. But that is not, that, as I tried to say, was necessary but not sufficient for this to happen. And it does not happen. Basically what you require is that a physical scattering process can happen at a point in the bulk. And the causally Euclidean sheet, that can never happen.
Yeah, okay.
Okay. The second limit that will be of great interest to me in this talk is the Regge limit. The Regge limit is defined as tau goes to 0, theta goes to 0, but tau by theta, which is some number which I'll call A, is held fixed. Okay. So in this limit on this cylinder, what's happening is that these 2 points, these P2 and P4 are coming sort of just above P3 and P1, and they're being separated in time by almost pi. Okay. In this limit, P3 and P4 become almost time-like related, and P1 and P2 become almost time-like related. And this causes sort of interesting things to happen. Okay. So in this limit where, remember, tau is being taken to 0, theta being taken to 0, but the ratio is being kept fixed. You can also work out the conformal cross ratios. Here the I epsilons will be important, so I've kept them. And I've just given you some formulas here. The thing to notice for now is just that we have that in this limit, sigma goes to 0, because each of z and z bar go to 0. However, their ratio doesn't go to 0. So e to the power 2 rho is something that is non-zero even in this Regge limit. Theta is the thing that's taken to 0 in the Regge limit. Okay, so this is the second limit that will play an important role in my talk. Okay, now let me quickly, like I told you why the tau goes to 0 limit was interesting. It's because of this bulk point singularity, and we'll see why that plays a role. But let me remind you about the significance of this Regge limit. When A is, you see, this Regge limit is parametrized by this number A, which is the ratio of tau and theta. And you can go back to my analysis of causal relations and check that when A is less than 1, the Regge limit lies on the causally scattering sheet, the one where we've taken z bar round 1 and z round 0. On the other hand, when A is greater than 1, okay, the Regge limit lies on the causally Regge sheet, the limit where we've the sheet where we've taken z bar round 1, but not taken z round 0. Okay, And okay. Now, so there are two, this Regge limit spans two different causal configurations and lies on two different sheets. So there's a Regge limit on the conformally Regge sheet, and there's a Regge limit on the conformally scattering, causally scattering sheet. Now, the limit, this Regge limit has been most studied, okay, in the regime where A is greater than 1. Oh, I forgot to tell you that at A equals 1, Z is equal to 0, and this is a slightly singular point. Again, that will turn out to be important as we go. So this Regge limit has been most studied in the A greater than 1 regime. This is where we are on the causally Regge sheet, where Z bar has been taken around 1, but Z has not been taken around 0. People who want to study this regime in conformal field theory normally consider the following insertions. They take operators 4 and 3 to be fixed at x equals 1, t equals 0, and x equals minus 1, t equals 0, and take 1 and 2 to start, at x smaller than 1, and then boost them. 2 is boosted in the future, and 1 is boosted into the past. Okay? And to start with, these configurations lie in the causally Euclidean regime. But as this line crosses this light cone, once this line crosses this light cone, there's a switch, and then configuration lies in this causally Regge regime. And when you do this, when you boost this and boost it very much, you enter the Regge scaling limit, the limit where sigma goes to 0, the cross ratio sigma goes to 0 on this. So this is a familiar configuration. So you can get to the same values of conformal cross ratios by doing this maneuver on one space and one time. And this configuration is much studied. I will come back to, for instance, by the people who study the chaos bound. We'll come back to this as we go, or maybe immediately. Okay. Any questions about the Regge? Excellent. So now the Regge limit has many interesting things going on, but the only thing that will be of interest to us is that the chaos bound gives you a strong implication for the scalings of correlation functions in the Regge limit when A is greater than 1. That is in the Regge limit on the causally Regge sheet. I'm going to very quickly remind you how that happens. Okay, you look at the correlation function here. This correlation function, in standard quantization, is just a time-ordered correlator. As I said to Abhijit, every correlator I look at in normal quantization will always be time-ordered. Okay? So if you choose time to run along, horizontal lines here, this is just a standard time-ordered correlation function. However, it was pointed out in the appendix to the chaos-bound paper that you can take the same correlator and view it not in standard time quantization, but in angular time quantization. Viewing this correlator in angular time quantization, you can see that this correlator becomes an OTOC. Okay, where you've got something inserted, and then something inserted at the same value of Euclidean time, but boosted in Lorentzian time. Then you got something inserted after a pi rotation in Euclidean time, and then two operators, once again something inserted just at Euclidean time, boosted in Lorentzian time. Going over this kind of OTOC contour. Okay, so the same correlation function here can be viewed as an OTOC correlator when viewed in angular quantization, where time is the angular direction. Euclidean time is the angular direction. Okay? And in this quantization, the ordering of the operators changes. Okay? It becomes an OTOC. It's not some time-ordered correlator. You get a different ordering of operators, but it's the same path integral expression. And then the chaos bound, which applies to how fast OCs can grow as you increase their time of insertion, okay, translates into the statement that this correlation function, hence this, this insertion, cannot grow faster than 1 by sigma cannot grow faster than 1 by sigma as sigma goes to 0 at any fixed value of rho. Okay? So, even though we're studying an ordinary time-ordered correlator, when we take time to be just running along ordinary time slices, there is a clever way to convert this into an OTOC, use the chaos bound to bound its growth as a function of this boost. Now, this boost parameter can be viewed covariantly and changed into a conformal cross ratio. And the chaos bound turns into the statement that if you look at this correlation function, it cannot grow faster. Okay, I should say that the correlation function normalized in the appropriate way, normalized by the product of 2-point functions. I've done that in this slide. That correlation function normalized in the appropriate way cannot grow faster than 1 over sigma in the limit sigma goes to 0. This statement can be translated into how fast it can grow with the boost parameter tau. It basically cannot grow faster than e to the power tau. I'm sorry I was a bit quick on that, but I'm going to have to hurry if I'm going to finish this talk. So I sped up a bit, but please ask me if there are any questions. Excellent. So this is for our purposes, the main importance of the Regge scaling limit is this, that in the region where the Regge scaling limit happens on the conformal, on the causally Regge sheet, that is this A greater than 1 part of the Regge limit, we have a sharp field theory bound on how fast operator correlation functions can grow. Okay, fine. I think that's all I want to say about, one last thing about kinematics. It's going to be important to this talk that the Regge limit and the tau goes to 0 limit overlap. And this statement can be quantified as follows. Suppose I take the expressions for the conformal cross ratios that I gave you in the tau goes to 0 limit, and then expand them to leading order in theta. You get the same answer as the conformal cross ratios that you get in the Regge limit expanded to leading order in A. Okay, so the part where A is small in the Regge limit is the same conformal cross ratio as the part where theta is small in the small tau limit. Okay, what's the way that I'm going to the thing that's going to be important for me is that there is, by working in the Regge limit, we overlap with the small tau limit, with the bulk point singularity. That's going to be important. Okay, fine. So this ends my review of the kinematics and the limits that I'm going to consider. Now I'm going to start the argument proper. Any questions? Also, organizer, please give me a deadline. Could I take 15 minutes more? Is that okay?
Yeah, you started 10 minutes late anyway, so 15 minutes.
Yeah. Okay, excellent. So now what we're going to do is this. Now we're going to focus our attention to a particular context. The context is the following. I'm going to look at focus my attention on correlation functions generated by a local bulk contact term via the ADS-CFT correspondence. So everything I said before this was just about conformal field theory. You could have done this abstractly. You didn't, except for the chaos bound, you didn't even need large N. Okay, but now I'm going to get very specific. I'm going to look at conformal field theories that live on the boundary of a local bulk dual theory. Okay, and I'm going to look at the correlation functions that are generated by bulk contact terms. Okay, it should be possible to generalize what we've done to exchanges, and maybe that will almost follow trivially, but we've looked carefully only at bulk contact terms. Okay. So any such correlation function takes the general structural form. They're a product of 4 denominators, which come from the denominators and propagators going from the boundary point to a bulk point x. And then since the correlation function was generated by some local bulk contact term, there's some polynomial expression in the numerator. That polynomial expression is polynomial of the bulk contact point and polarizations. Okay, now the analysis I'm presenting now is a small variant of the analysis in the by now classic HPPS paper. Okay, it's the study of the Regge behavior of correlation functions of this sort in the Regge limit. It's the small variant is going to be that, I'm going to be looking at it in both Regge limits, not just a greater than 1, but also a greater than 1 and a less than 1. And I'm also going to allow for polarizations, though the generalizations are pretty straightforward. Okay. So I want to understand how this correlation functions behaves as a function of cross ratios in the Regge limit. Okay, at leading order in the Regge limit. And following HPPS, well, the first thing I do is to note that in the strict Regge limit, if tau and theta just set to 0, it turns out that not just do we have P1 plus P2 plus P3 plus P4 is equal to 0. That's true for tau equals 0 at every value of theta. But when tau is equal to 0 and theta is equal to 0, you separately have P1 plus P2 is equal to 0 and P3 plus P4 is equal to 0. So now our boundary points, our boundary P's span neither an R2, 2 nor an R2, 1 in embedding space, but they in fact span an R1, 1 in embedding space at exactly theta and tau equals 0. Okay. With this in mind, it's useful to parameterize these bulk points in ADS as follows. I parameterize one of the time coordinates by u plus v by 2, the other one by v minus u, the other one by y0, and the space point, spatial points are parameterized by v minus u by 2 and y1 up to yi. Okay.
Sorry,
yes.
So when you say strict Regge limit, you also have in mind the bulk point limit, the overlap of the Regge limit and the bulk point
when I say strict Regge limit, I just mean theta and tau both equal to 0. Yes, it does overlap, but it's a very singular point. You need to blow it up. So I'm saying, but just as a kinematical statement, if we're at theta equals 0 and tau equals 0, these things happen. It's true, it also overlaps with the bulk point limit because tau is 0.
Okay.
Yeah. Okay. Now, these at u equals v equals 0. This is our parameterization in embedding space, and then we need to put in the ADS condition, the condition that x square is equal to minus 1. And that gives us a relationship between these y's and u and v. Now, when u and v are both 0, all the points in ADS in which u and v are 0 are orthogonal to all 4 p's, orthogonal to this full R11 in embedding space. Viewed as vectors in embedding space, these points are orthogonal to all points on this R11 in embedding space. If you think about it, what this means is that the manifold, the part of this manifold where u and v are equal to 0 is the part where light rays from boundary points can come and intersect. So light rays from boundary points can come and intersect on an HD minus 1 parameterized by these y mu points when u and v is equal to 0. Now, the reason that is important is this, where light rays, a point that is connected by a light ray to a boundary point P obeys the condition P dot X is equal to 0. But P dot X is what appeared in the denominator. Okay, so denominators blow up in this expression in the neighborhood of u and v is equal to 0. This suggests, and one can actually show, that in the neighborhood of this sort of Regge scaling point, u and v both being very small give you the dominant contribution to the integral. Indeed, in fact, you can show that the dominant contribution to the integral comes from u and v are of the same order as theta and tau. Okay, remember in the Regge limit, theta and tau were both small, both of the same order. Now, the dominant contribution to the integral comes from u and v both being of that same order. Okay, so because of this, what we do is to take the integrand, and this is just following the HPPS paper. We take the integrand and expand it in a power series expansion in these 4 small quantities, u, v, theta, and tau. To leading order, the denominators become this. Indeed, this is why u and v are of the same order as theta and tau, because the denominators determine what maximally contributes in the So that u is of the same order as tau, you can see from these expressions. Okay. And suppose your numerator here, now your numerator, okay. So what we do is to take this expression here and expand it in a Taylor series expansion of these small quantities. Now, we only keep terms to leading order. These denominators just become order theta, each of them. Okay. The numerator itself also has its own Taylor series expansion. We keep all terms of leading order in that Taylor series expansion. Now, you see, there are 4 small quantities in this regime: u, v, tau, and theta. And there are 4 denominators here. Each of the denominators is some linear combination of u, v, tau, and theta. So we can regard the small quantities not as u, v, tau, and theta, but the quantities that appear in the denominator. And the numerator then has a Taylor series expansion in these 4 quantities, the ones that appear in the denominator. Keeping leading order terms in the numerator, I mean, to leading order and smallness, all it does is cancel some of the powers in the denominator. And so when you look at the expression to leading order, I'm skipping some details. When you look at the expression to leading order, the u, v, theta, tau dependence of this expression is extremely simple. It's just powers of these fundamental expressions to some power, these fundamental expressions to some power, each of them. And then the homogeneity of this expression is something fixed depending on the scaling dimensions of your original operators, as well as the Taylor expansion of the numerator. Okay. Now, once we have, and then all of these Taylor coefficients here are functions of the remaining guys, the guys that are not small. For instance, the yi's, the parameters of where you are on the HD -1, as well as the polarization. So now we've got this expression. Each term in the integrand is very simple. And following HPPS, we can now just perform the integral over u and v. Okay, we can just perform the integral over u and v in this expression. I mean, it's more or less clear just from dimensional analysis, but you can do it very, very clearly. That what you pull out is an overall power of 1 over theta to the power 2b minus 2. This b is some combination of these various a powers and so on. Don't worry, it's some power, which whatever, some power times a function of a. And this function of a is something very explicit. It's given here. Okay. The only thing that will be of importance to us is that this function of a, at least from the part of the integration regime that's the function of a is only a function of a plus I theta. Okay, so physics tells you that what you're supposed to do is that in this Regge limit, if you're getting something from a bulk contact interaction, you get a power law in theta times a function of a, and the function of a is to be evaluated at a plus I theta. Okay, that's what I've written here. That's the net outcome of this analysis. Okay, almost all of it was in this HPPS paper. Perhaps the one new element that I've put in is to stress that this is true not just for a less than 1, not just for a greater than 1, which was the focus of the HPPS paper, but also for a less than 1. It's just the same arguments, it's just all those. Okay, and putting in polarizations and so on just doesn't change anything. Okay, so in the end, the outcome of that analysis is that in the Regge limit, we've got theta to some fixed power times a function of a. And a is analytically continued in a specific way. Now, recall that a less than 1 lies on the causally scattering sheet, whereas a greater than 1 lies on the causally Regge sheet. Okay? This function of a, just from the explicit integral expression here. Okay, this function of a, just from the explicit integral representation here. Here, this is integrated over the y's and so on. Is an analytic function of a that has singularities somewhere. In particular, it has singularities on the real axis at a equals 1 and a equals 0. A equals 0 is the bulk point singularity in the Regge limit. A equals 1 is the light cone singularity, is the singularity where Z was 1. This was this branch cut singularity that we encountered at Z equals 0. Z equals 0, the one that we went around to go from the causally Regge regime to the causally scattering regime. Okay. Now, this function here is something for A greater than 1, something for A less than 1, and has a singularity, a branch cut singularity at A equals 1. But it's completely analytic in the upper half plane. And indeed, physics tells us that what we should be doing is sampling this function, not on the real axis, but on the just above the real axis. Okay, so what we're supposed to do is to avoid this branch cut going over the branch point on the real axis, and that tells us that what this function is here for A greater than 1 is an analytic continuation of what it is for A less than 1. Okay, so I'm sorry this has gone fast, but let me just summarize the main points. What we've seen in the Regge limit is two very important things. First, that the correlator scales with theta or equivalently with sigma in a very simple way. If you knew nothing about the problem, you would think that, let's suppose that there's going to be a power law scaling with sigma, the power of that scaling will depend on rho. That does not turn out to be the case. The power of the scaling with theta, or the power of the scaling with sigma, remember sigma and theta are sort of proportional to each other in this Regge limit. The power of the scaling of our correlator with theta is a power which is just a constant that's independent of A. Now, the coefficient function behind this power is some function of A, which naively looks irregular at A equals 1. So you might worry whether what's happening here has anything to do with what's happening there. But when you go off into the complex A plane, the value of this function here is just the analytic continuation of the value of the function here, or vice versa. Okay, so the function here, the coefficient function, is connected by an analytic continuation between here and here. Okay, why is this important? This is important because the analyticity tells us that this h of A function cannot have crazy behaviors like theta functions in 1 minus A. And this in turn means that this power A here, the scaling power A, is the same on the causally Regge sheet and the causally scattering sheet. This is completely key because the scaling in the causally Regge sheet is controlled by the chaos bound. But we will be able to say something about scaling in the causally scattering sheet by looking at the bulk point singularity. So it's completely key that the power that determines the sigma scaling is the same on both sheets. And I've just given you an argument that it is. Okay, that's all I wanted to say about this. In the Regge, this analytic continuation in A can also be thought of in this way. At the beginning of my talk, I had this formula for this conformal cross ratio e to the power 2 rho, which was this function of A. And as we take A from infinity down to 0, in this e to the power 2 rho space, this is what we're doing. We're going like this around the branch cut. But e to the power 2 rho is just proportional to z. Z bar is not doing anything funny because z divided by z bar is e to the power 2. So the fact that our A was shifted by a positive I epsilon is the same as the statement that as we go from up to down on our cylinder, we're circling the branch cut at z equals 0 in the counterclockwise direction. Okay, so this analytic continuation in A is just a standard analytic continuation from one sheet to the other in conformal cross ratios. These are just different ways of saying the same thing. Okay, that's all I wanted to say about this causally Regge, about the Regge scaling limit. Any questions? Sorry for going so fast, but any questions? Okay, I'm afraid I've lost most of the audience, but let me just proceed anyway. Okay. Now let me focus on the other. Yes.
Sorry, slightly meta question.
Yes.
How do you think it could have failed? the
How
agreement
it could
on
have
the
failed had sigma been, had this theta power been a function of rho, a function of A. It's totally crucial that this theta power is a constant. As I will say at the end in the discussion section, in string theory, I don't think it'll be as simple as this.
I see.
Yeah.
Because of the alpha prime t piece.
Exactly. It's somehow the same statement that the Regge scaling is not controlled by a t independent number.
Okay.
Right? In fact, it's quite a miracle, right? If you just think of it, why should the theta power have been independent of Lilly? That is the key point.
So the Regge obedience of the string theory does not follow from this argument.
It does. Remember, we got it from demanding that there is a particular local bulk interaction that dominates the large energy behavior, the Regge behavior.
Okay.
Right. So if you have an infinite sum of these and they sum up to something else, anything could happen.
Okay.
Right. Okay, excellent.
This capital A was fixed by all those dimensions, right?
It was fixed by the dimensions and then what the numerators were doing.
So is it that, so that's, so in some sense, is it dimensional analysis that fixed this?
No, it's not exactly dimensional analysis. It's really, as we will see in a moment what it is, it's like the Regge part. You know, Regge scaling is not fixed just by dimensions because there's also T involved.
Yeah, but in a CFT with so this is, like you said, this is not applicable to string. I mean, it is not each individual. I mean, in string theory, you presumably will have a sum of such terms or something like that.
Right. So yeah, I see what you're saying. Yeah, but please go on.
No, so I was just saying whether this is
the fact that it's only one number of derivatives. The number of derivatives was fixed. That's what you're saying, right? In the bulk. Right. So you see, it's true that what's happening is this: that if you've got like a polynomial interaction in the bulk, one of the terms will dominate in the Regge limit, and that will have a fixed scale. So that's what's going on. The highest one dominates.
So if it was R to the 4, there'll be some corresponding numerator.
Yeah, now you would have, it depends on the polarization structure. This is what we looked at in our previous paper. Given any interaction, I could tell you exactly what its Regge scaling would be. But it requires more than dimensional analysis. It requires you to study the polarization structures for instance as well.
I think.
Okay, but it's something that can be done. Okay, but I will give you, so it's precisely whether we can apply our previous paper to this analysis, that is the question. And our previous paper studied scattering amplitudes. And here we haven't got exactly a scattering amplitude. So hang on for 5 or 10 minutes. You will see what I'm trying to say. It's very near to what you're saying.
Okay.
Yeah. Okay, great. Wonderful. Now, let me quickly go on to the next limit. The next limit is this bulk point limit. Okay. So in a remarkable paper already in 2009, Gary, Giddings, and Penedonnes demonstrated that a conformal field theory dual to local bulk theories have unusual singularities in row and 4-point functions. And for the special case that the external operators were scalars, they wrote down an explicit expression for the coefficient of this sort of bulk point singularity. It wasn't then called the bulk point singularity, but it was basically the same thing in terms of the flat space S matrix of bulk scalars. Now, as we are principally interested in the scattering of gravitons, we needed to generalize the analysis of GGP to the study of correlation functions of stress tensors. And we also did it for conserved currents. Now, the generalization involves a few extra elements having to do with the polarizations that had no counterpart in GGP. And we found it more convenient, we found it easier to use the method of the bulk point paper of Maldacena, David Simons Duffin, and Sasha Zhubayev. The details are a bit involved and are presented in our paper, but the final outcome is the following. In the kinematics that we are studying, in the tau goes to 0 limit, this should have been tau goes to 0, we find that the bulk point singularity, there is a bulk point singularity, and the bulk point singularity is given by a very, the coefficient of that, the leading bulk point singularity is given by a very concrete expression. I've written down the expression here in all detail. Rho, this is the singularity, the 1 over rho to the power something. Delta is the dimension of some of the external operators. The details don't matter very much. Okay. The important thing is that we have a complete understanding of the singularity and its coefficient. And the thing that appears in this coefficient is the integral over an HD minus 2, a hyperboloid, an HD minus 2 hyperboloid. This HD minus 2 is the intersection of the ADS D plus 1 hyperbola of ADS D plus 1 with the R D minus 2 that is orthogonal to the R2, 1 that is spanned by the insertion points at the bulk point, in the bulk point limit. And the integrand over this HD minus 2 is an S matrix of 4 particle scattering. So suppose we had 4 stress tensors, this would be an S matrix of 4 gravitons. Now, this S matrix, in order to make this S matrix a precise, to tell you what it is, I need to tell you what the polarizations of the incoming particles are, and I need to tell you what the momenta are. And here I give it to you in this slide. On this slide, I've given it to you in generality. This works for scalars, gauge fields, and gravitons. Here I specify the polarizations of the gauge field and the graviton. The polarizations multiply, oops, this HMN should have had a momentum as well, e to the pi kx. They multiply their momenta. And the momenta of the 4 different, let's say we're doing gravitons, are given by these formulas. Right. And this thing here looks like it's a function of omega, but we've assumed that the interaction has R derivatives in it. And that is chosen so that the omega powers cancel out. So this thing here, in the end, the omegas all cancel out. It's only a function of the thetas. It's only a function of the thetas. And the polarizations. Z perpendicular, I haven't given you all details, but it's the part of Z that is perpendicular to X. The point at which this integration is being done. And because Z perpendicular is a function of X, this S matrix here knows about where you are on this hyperboloid only through the projection of the polarization perpendicular to X. Okay. Again, it's a bit hard to absorb all details, but the important point is that there is a very explicit formula for the coefficient of this bulk point singularity in terms of scattering of particles with the interaction term that is causing this correlation function. Okay. Now, by looking at this explicit formula and sort of examining it, you can show the following. You can show that if the flat space S matrix generated by that interaction term were to scale like S to the power A in the Regge limit, then the scaling of this, okay, so now you take this bulk point singularity, which is computed at small rho, and then take its coefficient and expand that at small theta. So we're now in both the bulk point and the Regge limit. Okay, so you can show that if the scaling of the S matrix that generates this interaction term goes like S to the power A, then the normalized 2-point function, the normalized 4-point function, 4-point function normalized by the 2-point functions, okay, scales with sigma like 1 over sigma to the power A minus 1. This comes out of this formula. This is the scaling with sigma of the coefficient of the bulk point singularity. Okay, so that's the second piece of information that we need and that I've told you about. Any questions about this? Now once we have this, the argument sort of follows quickly. Okay, so let me just tell you the argument and then we can pose the questions. Okay, so now with these results in place, it's easy to argue that in the context studied in this paper, that is S matrices are scalars, photons, or gravitons generated by local bulk contact terms, the CRG conjecture follows from the chaos. Okay, recall that we found that in the sigma goes to 0 Regge limit, at generic values of e to the power 2 rho, the scaling of the correlator with sigma is proportional to 1 over sigma to the power A prime minus 1. Okay. On the other hand, when we first took the rho goes to 0 limit, that's the bulk point limit, and then the sigma goes to 0 limit, we found a scaling like, sorry, this should have been A minus 1, like 1 over sigma to the power A minus 1, where A is the CRG coefficient of the flat space S matrix. Now, if you look at these two statements together, you might think, aha, we're just going to the same point. We're first taking sigma to 0, then taking rho to 0, or first taking rho to 0, then taking sigma to 0. Doesn't this imply that A prime must be equal to A? This should have been an A minus 1. Okay, so you might have thought that these two things imply that A prime is equal to A, but of course that's not true. To see this, consider the following simple counterexample. Okay, consider the function 1 over sigma to the power A, rho to the power little a, plus 1 over sigma to the power A prime, rho to the power little a prime, with A prime greater than A, but A less than little a less than little a prime. Now, if we first take the small rho limit, okay, if we first take the small rho limit, this guy dominates, and the correlation function scales like, oops, getting it the other way around. If so, let's see what I've written. If we first take the small rho limit, the function reduces to this guy. Yeah, that's what it should be. We first take the small rho limit. Right, this guy dominates, exactly, because the rho is small. So this guy dominates, and we get the function scales. So we first take rho to 0, then take sigma to 0. We would find scaling like 1 over sigma to the power A. But on the other hand, if we first took sigma to 0, because now this is dominant, and then rho to 0, we would get 1 over sigma to the power A prime. So, you know, these two limits, rho goes to 0 and sigma goes to 0, needn't commute. And in general, they don't. But in this example, we see that while A is not equal to A prime is always greater than or equal to A. And that is a general feature that goes beyond this example. You see, because the way that A prime could be different from A is if the small rho limit came with a subleading scaling with sigma compared to the general leading sigma behavior. You know, A prime tells you what is the most singular behavior that you can have in sigma for any value of rho. It may be that especially at small rho, you have less singular behavior, but it can't be the other way around. So if you think about it, it's just a consequence of definitions that both in this example, but just more generally, A prime, that is the Regge growth, is greater than equal to the CRG growth. Okay, and now the theorem follows. A prime was less than equal to 2. This followed from the chaos bound. But A is less than equal to A prime. This follows from our discussion here. And therefore, A must be less than equal to 2. A was the CRG growth. And therefore, we have shown that if the chaos bound is obeyed, the CRG conjecture is also valid for the S matrices generated by those contactors. Okay, so I'm done. I'm really sorry for having gone so far over time. Very sorry about this. Let me end with 2 or 3 quick discussion points and then any questions. Of course, it would be great to generalize our discussion in many ways. First, we focused only on bulk contact terms. It should be almost trivial, I believe, but it should be done to carefully generalize this discussion to exchange diagrams. Next, it would be interesting to generalize our results to massive spinning particles. You know, we focused on conserved stress tensors and conserved gravitons for a certain technical reason. It would be a technically interesting exercise to generalize this to the discussion of scattering of massive particles. My suspicion is CRG holds for all kinds of particles, so it should be possible, but it was technically more difficult for reasons I could tell anyone who's interested. Next, in order of complexity, it would be interesting to generalize the results that we to see how the results work when the bulk is string theory. As I said in response to a question Abhijit asked, in this case, I expect everything to be more interesting. The analytic structure of correlators, correlation functions should be more interesting. Okay, it won't be just sigma to some constant power. And then, is it still true that there is a tight connection between scattering and chaos? How does it work technically? Next in order of ambitiousness would be to generalize the arguments of this talk beyond the large n limit. Recall that the chaos bound is in fact tightened at large n. Correlators are bounded by sigma to the power 0 in the Regge limit at finite end. Sorry, the chaos bound is in fact tightened at finite. Correlators are forced to grow even more slowly at finite end than they were allowed to grow at large. This suggests that we should be able to use the same techniques, maybe, modulo this business about complicated sigma dependence, sigma to some power. That's the key point. But maybe we would be able to use these same ideas to constrain the behavior of quantum S matrices and get things like the Froisson bound out of the quantum chaos bound. That would be interesting. Okay. And then it would be wonderful to be able to generalize both the chaos bound as well as the CRG conjecture in the study of correlators of more than 4 operators or more than 4 particles. And finally, it would be most satisfying to find an argument for the CRG conjecture directly in flat space and perhaps directly in the classical theory without invoking the superstructure of ADS-CFT, anti-de Sitter space, boundary field theories, and so on, perhaps along the lines of the signal problem. But I have nothing to say about that. Okay, thank you, and sorry for going over that.
Thanks a lot, Shiraz. That was really, really nice. Let's maybe unmute ourselves and clap for Shiraz. And we can take questions.
May I ask a question?
Yeah.
So Shiraz, I'm a bit confused about this argument towards the end where you show that if you take the bulk point limit first and then take the Regge limit,
yes,
you not do worse.
Yes.
Right?
Yes.
But if you compare this with a similar kind of scenario where, you know, a classical S matrix is allowed to grow faster than a non-perturbative S matrix, this kind of is confusing then. I mean, it seems that if you have infinitely many terms, you could allow for faster growth first by taking the bulk point limit rather than keeping the rather than not taking the bulk point limit.
Well, I think this would require your sigma, the sigma thing not to be a constant power. You see, if there is a constant power in sigma scaling, so what we demonstrate right at the beginning is that in the small sigma limit, at every value of rho, the maximum singularity is 1 over sigma to some power.
Yeah.
Then if we first take the rho goes to 0 limit and then take the sigma scaling, we might end up doing worse. We might be less singular, but we can't be more singular because the original thing applied at every value of rho.
No, but you know, non-perturbative S matrix versus tree-level S matrix. You have a non-perturbative S matrix that is supposed to grow only like S, while the tree-level S matrix can grow like S squared, right? So I'm
yeah,
just
but that's in different regimes, right?
Kind of,
the tree-level S matrix.
No, I'm just mathematically. No, I'm just mathematically. I'm just drawing the parallel. So here also, if you have infinitely many terms in the row sum, let's say you imagine some sort of power series expansion of rho, then it could resum to give you a result that is more singular in sigma.
It could resum to give you a result. I mean, at small rho,
sorry, what I mean is less singular in sigma. So if you do a small rho, if you look at small rho and power of sigma, that could be more singular than if you resum the rho series and look at the power of sigma.
Okay, let me think.
So
do a small rho and sigma. It could be it could be it could reduce the singularity, you said.
It could reduce the singularity the way non-perturbative physics reduces the singularity. I mean, this may be a vague parallel, but I'm just wondering if why such a kind of thing, such thing cannot happen.
Okay, let's see. You want terms that are increasingly singular in rho then. Is that right?
Yes, yes, yes.
But I've got the most singular term in rho. There's a limited singularity in rho.
No, not increasingly singular in rho. The power series expansion of rho should have increasingly singular terms in sigma, and then it could resume to a softer singularity in sigma. That's what I'm saying.
But that's okay. See, at rho equals, when rho is very small, this gives me the dominant behavior. This term gives me the dominant behavior.
Yes, yes, yes.
Okay.
Yes.
So if this term was worse than, you see, at every value of rho, the scaling cannot be worse than A prime. So that's enough for my argument.
No, so for example, what I have in mind is consider something like 1 over 1 plus rho sigma. Okay. Now, for a generic value of rho, this goes like at small sigma, it goes to 1. Well, okay.
See, it's important
okay,
for me.
Sorry, maybe I'm not.
Yeah. See,
yeah.
I think that if you allow for increasing singularities in 1 over rho, you could get funny things. But it's important for me that the leading rho singularity has been captured by whatever.
No, I was not necessarily saying that rho should have an increasing singularity. I was saying that coefficient of softer rho things could have increasing singularity.
No, but I don't think that makes any difference. You see, because I'm arguing that at small rho, I know how it grows with sigma. So at any other rho, it can only grow faster. That's all. So at very small rho, this dominates. And it grows with sigma like CRG.
Okay. Okay.
That's enough for the argument.
Okay.
Right?
Okay.
The fact that it dominates at very small rho is important. But beyond that, nothing more is needed.
Okay. Okay, thank you.
Yeah. No, thank you. Yes.
Shiraz,
yes.
So you said the exchange diagrams and the bulk should be much the same way, but I mean, like you said in the case, the tree level scattering, where you can have things which are sort of more singular than contact terms, that sort of thing doesn't affect, won't arise here?
You could have more singular, but the connection between scattering and Regge growth should be the same. So if the scattering amplitude is more singular, then the correlation will be more singular. But the connection should be the same. I believe that I haven't carefully established this, but I believe that it should still be true that if a tree level amplitude has an S matrix that grows faster than CRG, it will lead to a correlation function that will violate the chaos boundary, even for tree level scattering. I mean, that connection should be true.
So then,
but we haven't carefully established this, though it should. Though I suspect there's not much to do, but anyway, we haven't carefully looked at it. I emphasize this because Simon Karen, who contacted us and said that he thought that there may be subtleties with the with tree level exchange, which surprised me because I thought it would be a straightforward extension. Since he says this, I will look at it carefully. Yeah. Sorry, please go ahead.
So, but you're saying that the A less than or equal to 2 behavior is anyway a sharp kind of.
It's a sharp one, yes.
And so whatever singularity there is has to be always bounded by 2.
Yeah, right. What I call A prime. A prime is bounded by the chaos bound. Yeah. That is always less than or equal to 2. And then if it's still true for tree level exchange, which I strongly believe it will be, that A prime has to be bigger than
A will be less than or equal to A prime.
Yes, exactly. When it's true, then the connection, the CRG conjecture also follows for tree level exchanges. But we haven't carefully looked at that. There were 1 or 2 technical complications if you try to be careful. Naively, it works, but I haven't carefully looked at the degree of care that we have for this.
And then I didn't completely understand the statement about tightening the chaos bound. I mean, it seems to go the other way around, no? I mean, the Froissart bound is sort of S square log S square or whatever.
S log S.
S log. Oh, yeah. It's S log S.
Yeah. So it's, much below S square.
Right.
Right. And that's how the chaos bound also works, right? If you look at what people sometimes call the quantum chaos bound, which is really just a Cauchy-Schwarz inequality that the chaos bound people start their paper with. Okay. That tells you that at late times, the correlator cannot, at finite end, just cannot grow with any growth. And then in this intermediate regime, it means it cannot grow faster than 1 by sigma. But if you just take that original statement that it just cannot grow, very naively, it would translate into a bound saying that the S matrix cannot grow faster than S.
Okay.
Okay. Now that S we know is not exactly right? Froissart bound.
1 plus epsilon.
Yeah, there's something needs to be tightened there, but it's logarithmic tightening somehow.
Yeah.
I suspect it has to do with this sigma business, that when you include quantum effects, maybe the correlators won't be as simple as sigma to some power. But yeah, but I haven't thought it through very carefully, but I think it's an interesting question.
Okay, thanks.
In fact, it's a question Abhijit has emphasized to us a number of occasions.
Hi, sir. I had 2 vague questions.
Yes.
So first is about the last point in the discussion, whether there is some direct flat space way that we can get this CRG conjecture. So in recent years, people have, I don't know much about this subject, about what I'm saying, but in recent years, people have shown how scattering amplitude of massless particles is related to correlators of this weird CFT called celestial CFT, which is sort of like non-trivial CFT.
Yes.
So there's some CFT result which bounds correlators of the celestial CFT that can be directly translated into, let's say, the CRG conjecture.
Yeah, it's a great question. It's a great question, and I think I don't know the answer. I have 1 or 2 comments. One comment is the recent paper by Andy and Nima talks about the singularities that look like bulk point singularities in their celestial correlators. That felt like it had an interesting ring and maybe some connection. But the second comment, roughly along the same lines, is as follows. You see, in ADS, how were we able to make progress? There is one sheet on which scattering actually happens in the bulk. That's where you get the bulk point singularity.
Yes.
But there is another sheet, namely the causally Regge sheet, in which scattering doesn't happen. And it doesn't happen because it's not causally allowed.
Yes.
In this sheet, you take these insertions. There is no, maybe I should say it here. In this sheet, in this causally Regge sheet, the future and the past are so near to each other that there isn't time for particles to come out from the boundary points, bang in the bulk, and go back and reach the boundary in time to meet P2 and P4. Okay, but it's this place where we have a theorem. So we don't have a theorem where we have scattering.
Yes, I see. It's the Regge sheet.
But we have, so it's like somewhere else. We have a theorem somewhere and scattering somewhere else. And the point of our proof was the analytic continuation.
Yes.
Now, I wonder whether the same might be true in flat space. That it's useful to do the same thing in flat space. Now you could ask, what is the analog of the bulk point singularity in flat space?
Yes.
Well, okay. I think what you should be looking at, what you might want to look at, is correlation functions inserted on scri plus and scri minus, but inserted in such a way that they cannot quite scatter.
Like this, I mean, the light cone structure should be perhaps similar.
Exactly, like the conformal, and maybe there you can make sharp statements about the correlators and then analytically continue to the scattering point. But it's a great question. This is Tushar, right?
Yeah.
Hi, Tushar. It's a great question, and I think one might be able to make progress. But I don't really know how, but I think it's a great question.
Also, one more question. So let's say somebody just give you the chaos bound for 6-point functions. So is it then
Somebody
just
handed me what? The
chaos bound for higher point function, 6-point, 8-point, so on and so forth.
yeah.
So is it then just some technical complications as such as along the lines of this paper to get the CRG conjecture for higher point
Of course, I
function?
don't know if until we do it, but I suspect there's a tight connection. Yes.
Because yeah, okay, there is some papers which like try to hint at these.
You know, there are some papers that do that basically lump operators together. You make it effectively a 4-point problem and then proceed. If you're referring to those papers, I think there will not be enough information in those to do everything.
I see. Okay.
I mean, I think you will need at some point some genuine 6-point information.
Yeah. Okay.
But I'm not sure.
Okay. Okay. Thanks, sir.
Can I ask one question, Shiraz? So can I in this for these massive amplitudes, where is the technical problem? Is it between the link between the Regge and the scattering, or the?
No, it's an interesting thing. It's in the right. It's in the formula for writing the correlation, the coefficient of the bulk point singularity in terms of S matrices.
Okay.
You see, the reason for this goes as follows. Suppose you've got a massive particle. It has two kinds of polarizations, transverse and longitudinal. Okay. And as you know very well, or better than almost anyone, if you've got an interaction with a fixed number of derivatives, the longitudinal amplitudes scale faster with energy than the transverse amplitudes. Right? This is because when you go to very high energies, the longitudinal amplitudes are becoming almost pure gauge, because the massive theory and the massless theory are not very different.
Right.
But anyway, the longitudinal amplitudes are there. They're not pure gauge. They're not thrown away. They become very strongly coupled. Right? So this, fine. So now, even with a fixed amplitude, with a fixed number of derivatives, you get two behaviors in amplitudes, two behaviors in scattering amplitudes. Higher growth with longitudinal amplitudes and slower growth with transverse amplitudes. And then, while it's very easy using our method to pull out the S matrix of the longitudinal amplitudes from the coefficient of the bulk point singularity, it becomes harder and harder to pull out the S matrix of the transverse amplitudes, because they mix with subleading contributions from the longitudinal amplitudes.
Right.
Okay. And the subleading contributions are not quite longitudinal scattering matrices. They're longitudinal scattering matrices that see the fact that space is not flat, that there's an ADS space, there is some things. So none of it will in the end matter, but to make a proof, you will have to disentangle this.
Right.
That luckily was not there when you had a gauge theory, because longitudinal amplitudes were not there. That's why it was so easy with the gauges. Or a graviton.
I see. So the analog of this formula that you had for the coefficient of the bulk point singularity, that's the one that's.
Yeah, that is the problem.
That's the problem.
And it is a finite technical issue to clear up, but it's a pain. Okay, because what you want to do is to go in order to get the S matrices for the longitudinal amplitudes, you have to go to subleading singularities and then deal with mixing. So you have to solve the equations in that region very carefully, order by order and so on. I mean, a fair amount of work has to go into it. I think when you do that, it'll go away, or maybe there's some trick, but it's considerably more work.
Okay, thanks. There is a raised hand. Tushar, I think, wants to ask a question.
No, I already asked. That's
okay, fine. So Loga is next.
Yeah. Hi, Shiraz. So I had like some 2-3 questions. So the first, so you looked at this particular kind of a scattering where you're near tau equal to 0 and so on. But let's say in the global ADS, if I go to further, let's say negative tau, or
yes,
let's say minus pi, further,
yes,
and so on.
yes.
Do you think that there is a similar kind of an argument, or can you bound the growth there, or is it somewhat is it simpler, more complicated?
What to get this bulk point singularity, what you want is the scattering to happen. So if you go too far below, I think I haven't thought about it carefully. Okay, so let you may be asking many questions. One question you may be asking is whether bulk point singularities exist when you go further down. Let's say you keep the top two guys fixed and you go take the bottom guys further down, right? It's
probably,
yeah, go
on. I would naively think the answer to that question would be yes, right? You can scatter and then keep on reflecting or something like that.
Keep on reflecting, but the reflections would have to be pretty, maybe. It's a matter of examining I epsilons.
Right.
The I epsilons that I used assumed we were in this range.
Mm-hmm.
Okay, and the way it happened, I'll tell you technically. I don't know the answer. I'll tell you technically where that was used. It was used at this point that we were in this range, was that we can put a plus I epsilon everywhere.
Huh.
Actually, what you have to do, at least what we did to get this, was to continue the time, the global time, with the right I epsilons. And then when the signs in that global time had a particular sign, a particular plus minus sign, all these became plus I epsilon. That required everything to be in this 0 to pi range. I would have to rethink the problem in the other ranges. I'm not sure.
Uh-huh.
It's possible, but it's true.
But if there is a scattering, if this result is generally true for all sorts of scattering in ADS, then you would think that there is a bound there also. Is that?
But you're saying it would be a different scattering or just a periodically reflected same scattering somehow? I think that if there is a bulk point singularity, it will somehow be the same S matrix. And then just it's resonated back to where you are. I don't think there will be a new genuine singularity, new genuine scattering process, because these things are moving at the speed of light. They go in and come back out. They won't do it in more than time pi. Sort of.
So, but if it is a massive thing, it might be different.
But we're looking at the very high energy limit of these scattering amplitudes.
Okay, right, okay.
And then those just behave like massless guys.
Mm-hmm.
Right. So, right. If there is something like what you're saying, I don't think we'll carry new information. There'll be some resonances of an old thing.
Okay.
That would be my guess, but I haven't looked at it.
Okay. So second question, unrelated. So if I understood right, the last part of your argument, you were arguing that the scattering growth, if I can call it, is like subdominant to the
subdominant or equal to, yeah,
subdominant, or equal to the growth in the Regge regime.
Yeah.
Do you think this is true? Even, but there was an argument about power law. Maybe I think this was also probably the thrust of one of the questions that Abhijit was asking. But
yes.
but let me just ask it, yes, in the way I understand. Do you think this kind of statement is still true when both of them, are taken to string theory, where
there I don't know at all. You see, because in string theory, there's a key element in this argument, which says that the whole thing went like 1 over sigma to the power a, where a was a constant independent of rho. Okay. Now look what we need to do to go from where we have a theorem to where we don't. Okay. A greater than 1 is where we have a theorem. A less than 1, in fact, A is equal to 0 is where we have scattered. Okay. And this requires us to, in this e to the power 2 rho plane, go around this huge contour. So if the scaling with sigma is a function of rho, as I believe it will be in string theory, then all bets are off. Nothing subtle needs to happen. It's just that the first point, that the sigma scaling is the same here as there, it's just not true. You know, the sigma scaling could be 1 over sigma to the power f of rho. And then you get one thing here, another thing there. This grows fast, but that f of rho makes it slow down till when you come here, and there's no problem. Right? So this is a key question, I think. You know, the question is whether my argument was basically our argument is just some technicality that applies when you have, has limited range of validity, applies only when you have a finite number of derivatives, or whether there's a deeper connection between these two things. I don't know the answer. I don't know the answer. I suspect there's actually a deeper connection, but that requires, as we've discussed, a different kind of argument. Is that clear, Loga? The key point is the 1 over sigma to the constant. That is the key point that you get with this limited number of derivatives. That is not highly unlikely to be true in string theory.
Okay. Like you're saying, it is known that it is not true for, let's say, flat space things.
I mean, if the sigma to the power rho is a direct translation of 1 over of s to the power t, then we know it's not true there.
Right. Okay. But
it always goes the right way in string theory. Meaning, string theory obeys the CRG conjecture.
Okay.
Yeah, that's a good sign. So it would require some souping up of this argument, but maybe the souped up version is still true.
Yeah, what I'm asking is, so both of them go softer. Of course, they both of them, are in some sense better behaved than in field theory. Okay, both the scattering growth as well as the Regge growth. I was asking whether there's a sense in which the scattering growth is sub or dominant even in
Actually, in every example I know, in making my argument, I had this less than equal to. But in every example I know, the equality is saturated.
Like that's true for scalars.
It's true for scalars. It's true for gravity scattering.
Okay.
And I suspect that if we were to have worked harder, we could have shown that it's not just less than equal to, that it's actually equal to, in at least many situations. Let me explain what I mean. The bulk point singularity happens because there's a pinch singularity in these integrals.
Yes.
Okay. And when you look at this integral here, the thing that survives, there continues to be that pinch singularity. So even in the Regge element, the same mechanism that gave rise to the bulk point, it's the same mechanism that is giving rise to the bulk point singularity in the Regge element. So because we could get away without doing it, we didn't do it. But if we really had to, I think there may even be a way of tightening up this argument so that the A prime is not just greater than equal to A, but that you can show that in our context it's equal to A. That would be nice, because then it would make your question very precise. It would ask where you could ask whether there was a tight connection between chaos scaling and Regge growth of string theory. Not just an inequality, but an equality. Right. Again, I don't know the answers. I somehow think the answer even to this tight question will be yes. But I don't have a clue. But the people say things about this, right? There are the papers by Stanford and Schenker and so on, where their shockwave calculations tightly compute the chaos exponent from string S matrices. I think there's some evidence that it's true, right? But I haven't thought about it carefully. I wouldn't be willing to stick my neck out. But if you ask me to guess, I would say yes.
Okay. So a third question,
yes,
also unrelated to the first two. So this is about your comment, at the end, that about whether you can convert this into a statement about signal transmission and so on.
Yes.
Some causality. I suppose that's what you had in mind. So which I'm trying to understand So which side would you want to relate to causality? So there's a scattering side and there's a Regge side. Okay. And you think there will be an independent causality argument which will just constrain the scattering side directly, or it will constrain the Regge side, and then this
the way that
analytic continuation will help you?
The way that Sasha's signal model argument worked, it just did not look at the Regge side at all. It's just directly flat space S matrices.
Okay. Right.
Didn't use only causality, it used a bit of unitarity somehow. I mean, that's where this inequality that I started. Right. But it was some very general thing. So that would be the most satisfying thing, right? Not go around your neck and pull your left ear with your right hand and all of that. Just go directly at it. And Sasha, I think, almost has a proof along these lines. But yeah. I think the person, if Sasha's still on the call, you can ask. He would have the most insight into this.
Yeah, it's perhaps not. I think. Okay, good. Last question, and then I'll shut up. Okay, which is unrelated to other questions. So this is a question of, so do you think if you had like one, so you had all massless particles, but do you think, without, it would be good if you had like one massive particle, like say
one massive higher spin particle.
Actually, one massive higher spin.
Massive scalars are no problem.
Yeah, so one massive higher spin particle, let's say, which will be two guys, and then other being light, other being massless.
Yeah. In fact, I think exactly this case we could make the argument.
So could you kind of, do something?
Yeah, I think we could make the argument. Shuman, do you remember? I think you had the argument for this case. Is this right? Can you confirm? Shuman, are you on the call? Okay.
Hello.
Hi.
Hello.
Shuman, I don't know if you remember, but we discussed going to subleading orders, and we could go down one or two orders.
For the massive case, you are saying?
Yeah. So Loga's question is, say you have one massive particle, the rest are massless. Then can we make the argument? We require the problem was
somehow the ADS information is there, like in the subleading order.
But couldn't we go one layer down without trouble? I thought the trouble really happened 2 layers down. Or am I mistaken?
I see. For photon there. I think photon there is no problem. Yeah.
My memory is, I would have to confirm this, Loga, but my memory is that to go one step down, which was what all you need for one massive, would be not a problem. But if you're 4, if you have, I would have to confirm. I'm not sure. But I think it's okay. But if you have even 2 massive particles, I think you would have to do a lot of work or be clever.
Okay, thanks. Yeah.
Hello, Shiraz.
Yes.
So according to you, what's the most obvious way to generalize it to higher point functions? I mean, the bound to high, because then according to your intuition, then we may be able to rule out the chi-6 term. Right?
It sounds like we want some generalization of the Cauchy-Schwarz inequality that Maldacen and collaborators had. The key physical input was a Cauchy-Schwarz inequality. Right? And then after that, there was some complex analysis.
Yeah.
Okay. I sort of have the feeling that what you need is some 6-point Cauchy-Schwarz. I mean, something new. Not just bootstrapping the old stuff.
Would have more complex variables also, right? So
more complex variables.
It's a multi-variable complex analysis. Some new statement which doesn't simply follow from single variable complex analysis theorems or something like that.
I see. Thanks.
I have some questions for Shiraz, but I can ask him later on. It is a very vague question, so I think I'll.
But please go ahead, Gautam, unless.
Yeah. So you use two. Are these two independent techniques of like analytically continuing from one kinematic region, which we call the scattering region, to the Regge region? That's analytic continuation. The other thing is about using different time slicing, which that seems to be like a minefield of things to do. I mean, you have the normal Minkowski time slicing, and then you go to angular time slicing, and you derive such important results. So first of all, are these related? The analytic continuation thing and different time slicings, like horizontal versus.
So naively not related, because the different time slicings gave you results about a particular, for the different time slicing, you got a result just sticking in the conformally Regge limit,
right?
Causally Regge limit, without ever talking about scattering.
Right. Yes. Okay.
Okay. So this was a way of getting information about that Regge. Now, it's true that it was very powerful, but it was very powerful once you coupled it with the chaos bound.
Yes, of course. Yes, indeed. I mean, somebody has had to have proved something for the OTOC. Then you could.
Yes.
Right. So yeah. So I think this kind of question that Tushar has been asking is that suppose some stuff has been proved for the 6-point function.
Yes.
And then you sort of turn your time slices around.
Yeah.
And so on and so forth, and you can get. I mean, it seems to be like a real minefield of things to do. I mean, is it normally done, or you have done it? I mean, there is.
No, this angular quantization in this context was in the appendix of the chaos bound paper.
I see.
It was, standard for them.
I see.
Even well before them, Loga did something like this when trying to constrain fluid dynamics. Soon as, his relating coefficients in fluid dynamics to anomalies in a non-trivial way, he used basically an angular kind of quantization.
I see.
And again, got remarkable results. And basically, it's the same thing that we do whenever we go to Rindler space.
Yes, that's true. I did remember about Rindler. Yes, that's right. But this seems to be much, much, much more general.
Yeah, it's more because, right. It's more when you combine with the chaos bound. Yeah, right. Okay, maybe, yeah, I suppose. Maybe Loga has some comments. He must have thought, have you thought about this, Loga?
Yeah, I think it's a clever trick. I mean, the point is, but it is true that what Gautam says, that there are many more possibilities.
Yeah.
Like what helped us was that we kind of had an intuition for what we wanted to prove. And we just did the thing that was required to do that, and just did not go further. I think that's probably what the chaos bound people also. I mean, usually, like if you know what to prove, you can try to go a bit and then do some trick and come back. But you can ask, what is the general, universe of these tricks, and what kind of constraint that they impose. That's yeah. I don't know a systematic way of trying to answer that.
Yeah. A related question maybe is the following. This angular quantization clearly makes sense for a conformal field.
Yes.
Because it would be while equivalent to something with a non-contractible time cycle. But in an ordinary quantum field theory, this thermal cycle shrinks under angular quantization to a point. You might worry that causes trouble. You might worry whether does this quantization really require conformal invariance to make sense? Can you make sense of it without conformal invariance? Even this I'm not clear on. Loga, do you have a feeling?
I don't know. I think, okay, so at least the argument that we made assume that it's valid in quantum field theories, which are not generally conformal field theories. I think that is this thing, what we call as Euclidean consistency, which says that you can kind of take a Euclidean answer and interpret it in all sorts of ways, right? By interpreting different things as time cycles. I think it is fine. One particular limitation we found in our work was that, it gave some weird answers when you had things like gravity nodes and so on, things which are kind of somewhat at the edge of making, they're not quite quantum field theories, non-gravitational quantum field theories. I think the subtleties are of that form, in the sense that gravity or gravity no, which is kind of
But
things like that might actually. Yeah.
What about the origin though? Is there no possibility that there's trouble there? I mean, maybe not in hydrodynamics where things are slowly varying and so on, but what about the origin? Feels like a worrying spot unless you can blow it up, or not.
Yeah, the origin is also a point. In fact, in the argument that we made, the point is that you have to actually go beyond hydrodynamics, right? I mean, there is no
fast varying.
Yeah. There is no version of the argument which stays within hydrodynamics, because it's a relation, like the kind of relation that we were trying to establish, related
cross derivative order.
Cross derivative orders, things particularly things which you expect to show up at be subdominant, but actually like higher derivative orders, and those coefficients affect coefficients at leading order. Okay, like precautiously, so to speak, in derivative expansion. So that kind of thing happens because of what you said, this origin and things varying very fast.
Things vary infinitely at the origin, and that's not a worry.
Maybe. I mean,
okay, fine.
We assume that it doesn't. It is.
No, I understand. It worked beautifully for you, and what you did was certainly right. But I was just saying more generally. I mean, is there a clear angular quantization for it? I don't have a clear view.
I mean, in a certain sense, it's like going to a very high temperature, right? I mean, so, and one can argue that in some sense things become better. Certain,
I see. I see.
Even if the temperature is varying very fast, if it is very high temperature everywhere, maybe it's okay.
Yeah, but from another point of view, when you compactify, if you think of Euclidean space and you compactify on a zero-size circle, the field theory, the reduced field theory, becomes infinitely strongly coupled.
Right.
That might worry you. I don't know.
Yes, it becomes strongly coupled. Yes, but it as a field theory, it is. I mean, it's not like
infinitely strongly coupled. But anyway, this is so vague a discussion. Sorry.
Sorry. Yeah, I should also probably. Yeah.
Can I ask a question, Shiraz, about one of these points in the talk, where you look at the coefficient of the bulk point singularity and identify it with the scattering, right, as matrix?
Yes.
So that is just the sigma behavior.
That is the full sigma behavior is that of the S matrix. The full sigma behavior is captured at leading order and row.
Right. No. I mean, what does it mean to isolate the bulk point singularity? Could you elaborate? Because we want if the coefficient is to be the S matrix is a function of two variables. Right? So
excellent. So let's look at the formula here. So here, the S matrix here was a function of two variables, which you can say in many ways, but because of polarizations, we didn't try to get covariant. So it's a function of omega and theta.
Yeah.
But the final formula here, the omega dependence goes into the rho. I mean, suppose you assume that the number of derivatives in this theory, in the interaction was R. Okay. Then what appears here in the sigma dependence is S omega divided by omega to the power. But an omega scaling of S omega is just omega to the power. Okay, so it's like a non-dimensionalized S matrix that enters.
Okay.
Okay, so it's this angular dependence of the S matrix that feeds into the sigma dependence. And the part that was the omega dependence went into giving this power. That's where this R comes from. So it's like the energy dependence gives the strength of the rho singularity, and the angular dependence gives the sigma.
I see. So subleading powers of rho, if there are any, that would mean some derivative.
That could come from lower orders and derivatives, or it could also come from corrections to this basic fact. You see, at leading order in rho, this rho singularity is just as a bulk S matrix. But at one subleading order, there will also be corrections to this fact. Because in that order, the waves will start seeing that they're not propagating in flat space. They're propagating in a slightly curved space. And those corrections will feed into subleading powers of rho. So the whole subleading expansion will be an interesting one, and one that one could in principle work out, but I don't think anyone has done. So let's say we take a particular interaction with just R derivatives, not worry about the other interactions. Still, there will be a full subleading expansion. And the coefficients of those will not just be flat space S matrices, they will know more and more that you were in ADS space.
Okay.
You would have to solve the equations. Yeah, there's some interesting stuff to do there. I'm not sure if there's interesting physics, but there's an interesting differential equation problem to solve.
Yeah, understand. Thank you. Also, the connection between the Regge limit in the on the two sheets.
Yes.
The fact that it is the same.
Yes.
Could one also not see it from conformal block point of view, where you expand in S-channel conform blocks, let's say, and now the difference between the two causal sheets is that you are approaching OP singularity. So either from positive side or the negative side. Right. So it's just the additional e to the additional -1 that you keep getting in every conform block.
Right.
-1 to the power delta, something like that.
I see. So you say that I see. You're saying going around Z is nothing very dramatic. Z around 0 is nothing
dramatic.
Right.
Going around 1 and then going to 0 was a bit dramatic. The first thing.
Yeah.
The first Euclidean to Regge was dramatic.
Yeah.
Because going around 1, if you expand in S channel, then going around 1 is mysterious.
Yeah. Yeah. Right. I think this is basically the heart of the issue. That going around 0 is not a very dramatic thing, as you say. And that is the reason that we could go around 0 while always staying in the Regge. That was the key, right? We didn't have to go far away and then go around.
Right.
And that's more or less what you're saying. Now, I wonder if you can turn what you're saying into a proof. Maybe we can show that this kind of thing, once you sum all the conformal blocks, can reduce the behavior, the singularity, but cannot enhance it. A little like Hartmann's proofs.
Yeah, because you will get minus. So
because you get signs.
Conform block of spin L will give you sigma to the L or something like this, right?
Yeah.
In, let's say, Regge sheet.
Right.
And then in the causally, this thing, scattering sheet, you would get minus sigma to the L or something like that.
Now,
so
the only question is that but are the original coefficients all positive? Could it be that the signs actually enhance? If they were all positive numbers, then this is almost a proof. But I don't know enough about conformal blocks to know that. Do you know if that's true?
I know.
Shubham, do you know? Shubham, are you on the call?
No, not offhand.
Yeah, if they're all positive numbers for some reason, then what you've said is almost a proof.
I mean, positive numbers, if you have identical objects, then perhaps it is positive, right?
But even that is not so clear to me, because this is not about the original correlator, but it's about after having gone around Z bar equals 1.
Yeah, I think something like this must, I mean, if it is true, it should be there in Caramel's paper.
Well, after you go around Z equals 1, Z bar equals 1, each conformal block just picks up a thing like 1 by sigma to the power j minus 1. where J is the spin which is being exchanged. But
and then the number behind that, is that controlled?
Yeah, I think like you, at least in D equals 4, you can like you have an exact expression like.
Right. So maybe what you're saying is just true, Abhijit, and maybe that's a very simple general proof.
I mean, I thought that like, I mean, what I thought that like usually people talk about this Regge theories in this this conformal Regge theory paper by Penedones and all, where they actually managed to sum up, given a spectral function, they managed to give you the Regge trajectories, and it shows that it is bounded. I didn't understand what was the.
No, Abhijit's question was this. He said, let's take a given conformal block. Then we go around Z bar equals 1, then we go around Z equals 0. The going around Z bar
S-channel conform block.
What? Exchange conform block, yes.
So S-channel conform.
Yes. S-channel conform. Yes. We go around sigma equals Z bar equals 1, that does something crazy, like the thing you're talking about. But then going around Z equals 0 shouldn't do much because it's an S-channel conform block, just gives you a phase.
Correct.
Now, so his point was that if the original, let's say we're exchanging identical particles.
Yes.
And if the original conformal block then came, after going around Z bar equals 1 came all with positive sign or the same sign, then picking up funny signs can only reduce the absolute magnitude. And then that will basically tell you that it cannot, that the small sigma behavior softens.
I see.
It sounds very interesting to me.
Yeah.
I don't know enough to know whether it's true or not, but it sounds interesting.
I mean, sorry, Shiraz, just to confirm that whether I was following this discussion. So if let's say what Abhijit is saying is true, that it works like say for a particular conformal block, would that mean that you would have shown at least when a particular conformal block dominates, that the scattering growth is
equal.
Cannot be.
One block dominates, it will be equal because it's just a phase. But more generally, what Abhijit's suggesting is true, including the signs, that the original thing came with a positive sign or the same sign. Then you would have got much more. You would have got a statement even, in much greater generality. Because you're just using something like absolute value of sum is less than sum of absolute value.
Right. Yes. So, okay. So if it is a finite number of conformal blocks.
Or even infinite, I think, as long as it's convergent.
Right.
Very similar arguments were used by Hartmann to do this causality stuff.
Right.
Yeah. Sorry, somebody was saying something. Was it Gautam? Somebody was saying something and I interrupt rudely.
Sorry, yeah, I was just saying that like I maybe a naive question regarding this conformal block question. Like, what would happen for the cross-channel blocks? Like, so this we think of the Regge limit as, this is one question that maybe Abhijit knows. In the CFT Regge thing, like in the CFT Regge limit, what is like? I mean, do the cross channels don't contribute to the Regge growth?
No, okay. So I don't remember this very well. Okay, so I probably will end up embarrassing myself. But I mean, but the thing is, let's say you want to take the Regge limit, which is let's say Z and Z bar both going to 0, sigma going to 0, right? So Z bar both going to 0. But before that, you take Z bar around 1.
Yes.
Now, clearly, in order to do this on a correlation function, the convenient expansion to work with is the S-channel expansion.
Yeah.
Because you want to take things to 0 later on, right?
Yeah.
Maybe you are asking what if you take the expansion around T-channel? Right. That is something where the first monodromy would be easy to do. but the next step of taking this to 1 would be a little bit not under
It would not be a good strategy because we're trying to relate things by around 0. So you're free to use either, but why not use what's simple? I think is what Abhijit said.
Yeah, right. So now in such a case is what is done usually, this taking the HTML block, and then I think the statement is that when you do this monodromy and try to take both of these to 0, then the singularity is controlled by the spin, right? Sigma to the L, L or something, L minus 2 or something like that. So each individual block contributes, high order singularity.
Yeah.
Right. It's like a exchange of a spin L particle contributing to S to the L growth or things like that. And then the idea is that this sums to a smaller behavior. I mean, a better behavior.
I mean, it seems to me the key question is the signs. Right?
Yeah, I agree with this. There was some statement about the signs, I think.
I think it's very interesting. If there is a clear statement, then it has the potential of taking it well beyond what we did. This may work, we, for instance, it might work in the string theory example, right? Right. We couldn't say anything about the string theory scattering, but this is such a general thing that.
No, but then there was another limit also, right? In between, you have to take the bulk point limit, right? So that kind of a question is still there, is it not?
That's also true.
That's also true. This is about the side. It's about the side on which you are approaching, but you have to take the row going to 0 first, right? I mean, if you want to connect it to the scattering,
right? But
then
suppose you are able to effectively prove that in going from, let me show the diagram. In going from here to here, the sigma to the power function of rho, that function of rho is a function of rho, but it's a 1 over sigma to the power function of rho. If you can show that is a decreasing, f of rho is a decreasing number.
Yeah, right.
Right? Then this part is controlled by scattering. This part is chaos bound. So you've got an inequality. I think it's a key question. We had it so simple because it was just the same. But I think what you are trying to do, Abhijit, is to say, well, in some situations it won't be the same. We know that, like string theory. But anyway, there's maybe some monotonicity.
Yeah.
That sounds very interesting.
Right.
Yeah, we were in the baby example, but there's a whole world out there that's more than what we did. I would be great to understand things.
Okay. And then would this not go towards the non-perturbative thing also?
Yeah, I think so. I think so.
Because you don't have to directly from the CFT point of view, right?
Yeah. It wouldn't that be fascinating? It's the kind of thing people may have looked at or not. Sandeepan was telling us about some things like this. I'm not sure. The people who know about CFT should tell me, how much has this going around Z been studied? Maybe it's not a question of interest to many people, and therefore there's lots of.
What I've seen is mostly the first monodromy, the first 2 sheets.
The Z bar.
Yeah, bulk point, very few people have.
Yeah, so maybe that's just some low-hanging fruit there. Something very simple to say, if you just look at it. It sounds very interesting to me.
Yeah, okay.
Maybe we're wearing out our welcome here.
Sorry, could you, Shiraz, one question. So this kind of thing would be a bound on, let's say, some sort of a quantity in ADS, right? So in order to connect it to the flat spaces matrix,
in the string theory example.
Sorry,
yeah. So I agree. There are two questions. One question is, is there a clear, in the particle case, you went to high energies and that was going to flat space. Right? Now you may worry that in the string case, that's not the case. Right? Because strings are big and they see the space. And sometimes in some contexts, the higher the energy, the bigger the strings. Right? So that is a legitimate worry. On the other hand, there's this flat space limit.
Right. Yeah. Where you kind of take energies greater than the ADS scale, but not the string scale.
Right. It's believed that it's possible to go to string theory in flat space, right?
Yes.
Yes,
people do work on this kind. Yeah. People
in that limit,
these results.
This should be uncontaminated by ADS. So since that is believed to be possible, I think there's something one should be able to do.
Like, can one also maybe connect it to like things like which are rapidly spinning and,
right,
PP wave, that kind of old story.
Sorry, just one quick statement about this. In what we had to do, all we had to do, we worked in a theory that was at some fixed coupling. Now, because the bulk theory was local, that coupling was, of course, secretly infinite. But we didn't need to put that in. So what will be needed to do would be to take the size of the sphere to infinity in string units, very explicitly, if you want the string theory thing to become flat space. So it won't be enough to go to high energies compared to ADS units. You also have to take the there's a new dimensionless parameter, right? Size of the, say, ADS in string units, and that will have to go to infinity. And that's basically the flat space limit. Yeah, so we'll need. So in what we did, we didn't need to say any of that because nothing mattered.
Yes.
You would have to put that in. We'd have to do a little more detail then. Sorry, Loga, I interrupted you. Please ask again.
No, I was just asking whether there is a scattering version of something like BMN story, like where one looks at, one takes a limit which kind of looks at dimensions and so on. I mean, one usually thinks about it in terms of Euclidean statements, but the question is whether you can make a statement if you can kind of take some spinning limit and do something so that you are basically probing flat space string theory. Whether there is some statement like that one can make. Because in BMN story, at least to the extent that I understand, that's what happens, right? In some sense, you effectively are doing flat space string theory from n equal to 4. Right. But as far as I know, it is usually it's stated in terms of anomalous dimensions and just dimensions of operators and matching the string spectrum to the dimensions of operators and so on. But that's a basically a Euclidean statement. But the question is whether you can say something about, I don't know whether anybody has studied endpoint functions and so on in that limit. Maybe Shiraz, maybe you might know better. But
people look at that kind of thing. But I think you're asking, Loga, whether, for instance, even in the spectrum, you're asking about scattering. I see. You could ask, should we expect any particular modes, their S matrices to behave like S matrices of flat space, even when ADS radius is finite at high end?
Yeah. Yes. at least BMN tells us that the as far as dimensions are concerned, okay, like for a corresponding Euclidean question, the answer is yes, in a certain sense. If you look at
it was very confusing, right? There were the claims that it was yes, and then there were claims that it was no. And the original match between weak coupling and strong coupling turned out to be a bit of a coincidence.
Right.
Yeah, I mean, it was a very confusing. A lot of BMN has been subsumed by the integrability story.
Yes.
Okay, so we could ask, in the integrability story, at finite lambda, is there any sector that behaves like string theory in flat space?
Right.
I doubt it somehow. But yeah.
I mean, one fantasy would be that, like somebody just solves at least some scattering problem with sufficiently supersymmetric or something, like all lambda.
Right.
And then, like you can kind of just look at the small lambda and match it against perturbation theory and large lambda and see some Virasoro Shapiro or something. I don't know.
Right. Right.
But
right.
Of course, nobody knows how to do that as of yet.
I mean, you could wonder whether it ever happens that something is dominated by being point-like. It's really that, I think, physically, that if you spread out of order string scale, I mean, of order 1, then finite lambda will differ from flat space. But if there are some sector that really remains point-like.
Sorry, I thought you want to get string theory in flat space, right? You want to take a limit in which you get a string theory in flat space. So why do you say point-like? I mean, you do want.
I was wondering whether there were some modes that behaved that they were like they were point-like. Some special highly spinning things or something, highly rotating, fast rotating things that effectively behave point-like. Because otherwise, it's not going to work at finite lambda. Once something spreads out, it sees the difference between ADS and flat space.
Yes.
I don't know about that.
I think we're trying to solve a lot of things here.
Yeah.
The chair is very lenient.
Maybe the chair has left.
No. It's yeah.
Sorry
it's been a very, very nice discussion anyway. So I have no problems being cut off. Thanks a lot, Shiraz. It's really
no, thank you very much.
Nice.
Thank you for the opportunity.
And if you guys want to continue, we can